చదువుతున్న థర్డ్ యూనిట్ అన్వర్డ్స్. ఓకే, సో ఈరోజు టోటల్ 5th యూనిట్ టోటల్ ఫినిష్ చేద్దాం. ఏమైనా డౌట్స్ ఉంటే మీరు అడగండి. 5th యూనిట్లో నేను కంక్లూడ్ చేస్తాను. సో ఆఫ్టర్ దట్ టుమారో ఆన్వర్డ్స్ రివైజ్ ద topics. So whatever you have the doubts, you can ask. Okay, so in which topic you have doubt, so I will explain the topic again. So if anyone have any doubts on the topics, you can ask. ఏదైనా టాపిక్లో మీకు డౌట్ ఉందా? ఓకే, సో మీకేం డౌట్ లేవు. ఓకే, ఐ విల్ ఎక్స్ప్లెయిన్ యూ టుడే regarding about some remaining small topics are there in that. So I will explain that 5th unit, the small topics. So why I didn't tell this ferroelectric means, so after completion of the ferromagnetism, so I want to explain this ferroelectrics. That's why I didn't explain you. Just so this is not that much important. Just definition as well as you have to know the definition. What is the ferroelectrics? Okay, that's why I have to teach you ferroelectrics. Now coming to the ferroelectrics here. When a dielectric material exhibit electric polarization even in the absence of external field, this type of materials we will call it as ferroelectric materials, and this phenomena we will call it as ferroelectricity. Understood? So actually, if you will take dielectric material, if you place in external magnetic field, what happen? Polarization will occurs. Polarization will occurs. But in case of some materials, without applying any external electric field, polarization is occur. These type of materials we will call it as ferroelectrics. Okay, generally we know that in case of dielectric material, if you apply the electric field, what happen? Polarization occur on the surface of the dielectric. Okay, so in case of ferroelectric material, without applying any external field also, your polarization will be takes place. These type of materials are called as ferroelectrics, and this mechanism we will call it as ferroelectricity. Okay, what are the examples of ferroelectrics? What are the main examples here? So barium titanate, BaTiO3, barium titanate, as well as rock salt and potassium niobate. So these three are the examples. For so barium. So main first example is barium titanate. Main example is here barium titanate. So barium titanate is the best example for ferroelectric material. After that, rock salt and potassium niobate. These three are the examples for ferroelectrics. See here, we will see the some properties. So first of all, if you will case polarization, due to that polarization, what is the dielectric constant will be takes place. So already we said that permeability, ratio of the permeability. Okay, so that ratio of the permeability of free space and in material, that is called as dielectric constant or relative permeability. Okay, that dielectric constant value in case of ferroelectric material, so that is very high. So if dielectric constant is high, means that is polarization of that material is very high. Okay, dielectric constant is high means so polarization of that material is very high. The dielectric constant reaches to the maximum value only at a particular temperature called Curie temperature. Similarly, in case of ferromagnetic material, what happened? That magnetism will be with increasing the temperature, that magnetism will losses. After that, so what happened? At a particular temperature, it will behave. So below that temperature, it will behave as a paramagnetic material. Above that temperature, those will behave as a ferromagnetic materials. Here also, in case of ferroelectrics also at a up to particular, with increasing the temperature here up to particular temperature, the dielectric constant is maximum. After that, so it will suddenly decreases. The dielectric constant suddenly decreases. This temperature we will call it as Curie temperature. Curie temperature. At which temperature? So the dielectric constant suddenly decreases. The temperature we will call it as Curie temperature. Okay, now coming to the polarization does not varies linearly. So with respect to the electric field, hence these materials are also called as non-linear dielectrics. Okay, now coming to so these ferroelectric materials are non-linear dielectrics. What we said that so actually, so at a particular temperature, this dielectric constant is called constant, the maximum. After that, it will be reduces. So the temperature we will call it as Curie temperature. But with increasing the temperature, these will not increase linearly. Suppose, yeah, it will be like this. Linear means so it's straight line. It will be a straight line, but it will not increases linear. Okay, it will be may increase up and down. Okay, at a particular temperature it suddenly decreases. Okay, so that means that it is not increasing linearly. It is not increasing linearly. Okay, hence these materials are also called as non-linear dielectric materials. So that's why, so the dielectric constant is not increasing linearly with increasing the temperature. It will be so at a certain point it will be maximum. After that it will be increases and decreases. Okay, after particular temperature and it reaches to the maximum and suddenly goes to the lower value. Okay, that temperature Curie temperature. Okay, now after that Curie temperature, dielectric constant is very low. Okay, now coming to so they exhibit electric polarization in the absence of external field. We know that. So the exhibit domain structure and hysteresis similar to the ferromagnetic material. Already in ferromagnetic material, we'll discuss about the how domains will be oriented. Domains will be oriented as well as hysteresis loop also we discussed. In case of ferroelectrics also same. So that means each atom will act as a one dipole. So like in case of how it will be ferromagnetism, so domain will be there. Similarly here in case of ferroelectrics also, so there are certain domains will be there. Okay, so based on that domains, they will exhibit without applying any external magnetic field, those will exhibit the ferroelectricity. Ferroelectricity. Now coming to so this is about the ferroelectrics. Now coming to the piezoelectrics. So piezoelectrics. So piezoelectric materials are also exhibits a permanent dipole moment. Permanent dipole moment without applying external field. So but how means so if you apply any mechanical work, if you mechanical work is done on that material, that mechanical work is converted into what is the charge means so polarization will be takes place due to the so due to that mechanical work is here converted into so charge. How it will be takes place means if you will take any dielectric material, that means piezoelectric materials are dielectric materials only. If you apply the mechanical pressure here, because mechanical pressure, if you apply the mechanical pressure means what happened automatically, so due to that mechanical pressure polarization is occur. Okay, so due to that polarization what happened, electric field will be developed. Okay, so based on this technique, already we know that so Shirdi Sai Baba temple is very famous. So and that temple while సో మనకి భక్తులు నడుస్తున్నప్పుడు ఎలక్ట్రిసిటీ ప్రొడ్యూస్ అవుతుంది అని ఎలక్ట్రిసిటీ ప్రొడ్యూస్ చేశారు. సో ఎలా అంటే సో బేస్డ్ ఆన్ దిస్ ఫిజియో ఎలక్ట్రిక్ ఎఫెక్ట్. సో ఆల్రెడీ walking shoes also there. So while walking automatically some electric field will be produces in that walking shoes. Okay, so based on this piezoelectric effect, so they will take the piezoelectric materials. So if you apply the mechanical stress, automatically they will be polarized. Okay, these type of materials we will call it as piezoelectrics, and this mechanism is so piezoelectricity. What are the examples? Quartz, lithium niobate and barium titanate. Okay, these are the examples: quartz, lithium niobate, and barium titanate. These are the examples for piezoelectric materials. Piezoelectric materials: quartz, lithium niobate, and barium titanate. Okay, so when we will apply the mechanical pressure, polarization will be takes place. Polarization will be takes place. Okay, so due to that polarization, what happened here? So some electricity, so potential will be developed. So due to that potential, so some current is flowing through the circuit. Okay, so this is the, so due to the mechanical pressure, some electricity will be produced. So this mechanism we call it as piezoelectricity. These type of materials are piezoelectric materials. Examples of piezoelectric materials are quartz, lithium niobate, and barium titanate. Okay, now this is about the ferroelectrics and piezoelectrics. Okay, so once again I want to explain here domain theory. Domain theory. Okay, domain theory of ferromagnetism. Ferromagnetism. Okay, they will. So in case of ferroelectrics also domain theory will be same. So just you replace it. So instead of ferromagnetism, just you replace the ferroelectric. Okay, so they will not ask about the hysteresis and domain theory in ferroelectrics. Only they will ask hysteresis loop and domain theory only in ferromagnetism, ferromagnetic materials. Okay, that's why. So I will explain you. This is very important one. That's why I will explain you once again this domain theory. Okay, domain theory they will ask directly. So explain the domain theory of ferromagnetic materials. Otherwise, so they will ask how it will be means explain the hysteresis loop while using the domain theory. Domain theory. So at that situation also, so while using domain theory, you can explain the hysteresis loop. Okay. Now coming to the, if you will take ferromagnetic material, that maximum ferromagnetic materials are the single crystals. Okay, single crystals. If you have multiple crystals, that means polycrystals. Polycrystals means so they chance to exhibit the already anti-ferromagnetism or ferrimagnetism. Ferrimagnetism. So but so maximum all type of ferromagnetic materials are single crystals only. Single crystals only. So that single crystals of ferromagnetic materials are divided into large number of small regions. Okay, these small regions are called so domains. Once again, a single crystal of ferromagnetic materials is divided into large number of small regions. So these small regions are called domains. See this. So this is one domain, this is another domain, this is so one more domain like this. So here different domains will be oriented in different directions. So what is the domain? I will explain you. Now this is the domain here. So what is the domain means here small region we will take. What will be there inside the domain? Here each domain contains so approximately 10 to the power of 17 to 10 to the power of 21 atoms. Each domain contains so 10 to the power of 17 to 10 to the power of 21 atoms. Okay, whose magnetic axis, that means each atom will act as a one dipole. One dipole means so dipole having north pole as well as south pole. Each atom have one dipole. So that's why so they will exhibit the magnetism. Each atom exhibits the magnetism. So those magnetic axes are aligned in the same direction. So if you will take one particular domain, so one particular domain here approximately 10 to the power of 17 to 10 to the power of 21 atoms are there. So those each atom will act as a one magnetic domain. So those magnetic axis will be aligned in a same direction. If you will take one particular domain, all atoms magnetic axis is same direction. Same direction. Their magnetic axis are aligned in the same direction even in the absence of external field. External field. Okay, but here each domain, if you will take each domain having particular magnetization in a particular direction. If you will take this domain, so these are domains oriented in so this direction. Okay, this direction. Similarly, So these domains orient in a this direction. These domains orient in a this direction. Okay, different domains will orient in a different direction. That's why what happened here, resultant magnetic momentum without applying external field, resultant magnetic momentum is zero. So see here, individually they have permanent magnetic moment. Each domain have so permanent magnetic moment, but if you will take resultant magnetic moment without applying any external field, resultant magnetic momentum is zero. Okay, suppose if you will take iron, so iron means without magnetization, iron doesn't have any magnetism. So if you magnetize it, what happen, so all domains orient in a field direction, that's why so it will be magnetized. So after magnetization they will exhibit the magnetization, they will exhibit the magnetization. How they, those material will lose the magnetization, how those material will lose the magnetization means, if you hammer it, so take the iron, after magnetization if you hammer it, if you hammer it means, so automatically those material will lose the magnetization, lose the magnet. That is the one process. If you apply the any stress or strain, so they may chance to lose the magnetization. If you apply the magnetic field in opposite direction, may chance to lose the magnetism. So there are so many ways to so demagnetization. Okay, so this is about the so how magnetized material means, if you apply the magnetic field, so in that particular direction all domains will be oriented. So because of this reason, so that will be magnetized. After removing the external field also, so those domains does not comes to the their original position. So some make chance to come, but the maximum domains does not comes to the their original position. So that's why here, so they will exhibit the so permanent magnetic momentum after magnetization. After magnetization. Okay. So if you will take hard magnetic materials having, so it's required very huge field uh, to remove the demagnetization. So that means to remove the magnetic field, induced magnetic field inside the material, it will require very huge magnetization. That's why so permanent. So if you want to prepare the permanent magnetic material, so they will use the hard magnetic materials. Hard magnetic materials. In case of soft, already I explained yesterday. So what about the hard and what about the soft? If you will take soft, if in case of hard magnetic material, that hysteresis loop will be very high. In case of soft magnetic material, the hysteresis loop area is very small. Okay, so demagnetization is very easy in case of soft magnetic materials. Okay, so now coming to the our topic. Yeah. However, in the normal state of these substance, the different domains are randomly distributed. Hence, the resultant magnetic momentum in the any direction is zero. Okay, already we discussed. So, if you will take resultant magnetization is zero. Okay, without applying any external field. After applying the external field, so these all domains orient in a field direction. That's why those will be magnetized in a particular direction. Okay, whatever the applied direction, those will be magnetized on that particular direction. Okay, now coming to the so how, yeah, so how those will be magnetized. So based on the domain theory, I will explain you. So based on the domain theory, how material will be magnetized. So according to domain theory, there are two processes are there. Two processes are there. So one is the by displacement of boundaries of the domains. By displacement of the boundaries of domains. Okay, so these are the boundaries here. See here, so this is the boundary, similarly this is the boundary, so this is the boundary and this is the boundary. If you apply the magnetic field in a particular direction, so this direction I will apply the magnetic field. What happened here, so according to that, so displacement of domains according to first point is, so the displacement of boundaries of the domains. That means if you apply the magnetic field in this direction. What happened? So this boundary, in particular, what is the direction? This direction, it will be same. Similarly, approximately this direction. So these directions, whatever it will be there, according to that direction, it will be increases. See here. So this and so approximately this. So these domains are domain walls are increases according to the so applied field direction remaining. So this is the opposite direction of the these domains are opposite direction of the field direction. So these will be decreases. This boundary of the area of the this boundary will be decreases. Remaining area, so parallel to the direction. This is parallel to the direction. That's why. So these domain walls are displaced. So to this direction. To this direction. Okay. So similarly, so these domain walls are increases. These domain walls are increases, and these will be merges. So if you apply the maximum field, if you apply the maximum field, so all domain walls are merged with each other. Okay, that means because of the displacement of the domain walls here, these materials are magnetized. These materials are magnetized. So at which cases these domain walls are displaced? That means if you apply the small magnetic field, if you apply the very small magnetic field, what happens? Instead of the rotation of the these domains, instead of the rotation of these domains, just domain walls will be moved. Just domain walls will be moved if you apply the so small magnetic fields. Small magnetic fields. Okay, next process. So this is the first process. What is that first process? So by the displacement of the boundaries of the domain. Okay. Now second process, the rotation of the domains. The rotation of the domains. Okay. Now how it will be rotated? Yeah, I will explain you while using the diagram here. See here, without applying any external field. Okay. Here domains are oriented in a different directions. So resultant magnetic momentum is 0. Now if you apply the very small magnetic field already we discussed, so boundary displacement will be takes place, because so if we are applying here, so magnetic momentum in this direction, so in this direction applied magnetic field will be applied in the so like this direction. That's why what happened here. So this is the field direction. So this is the this domain having field direction. That's why so this domain wall is increases. This domain wall is increases. So this is the opposite direction of the field direction. That's why what happened. This domain wall will be reduced very small compared to the remaining all domain walls. So like this, so displacement of the boundary displacement, this process we will call it as so boundary displacement. See here, so parallel boundary, this is the parallel boundary. This parallel boundary is increases, so with increasing the magnetic field, okay. So in this slow process only, if you increase the magnetic field slowly, very slowly means, so this boundary displacement will occurs. Okay, now coming to the domain rotation. If you apply the so very high magnetic field at a time, if you apply the very high magnetic field at a time, what happen here? So domains, so if you will take, this is the domains. In this domain, so many number of atoms will be there. Those all atoms are oriented in a field direction. All atoms are oriented in a field direction. Okay, and these materials will be magnetized. So if you apply the very high magnetic field, so this rotation of the domains will be takes place. So this is the rotation of the domain. All domains, previously only this domain is in this direction, remaining all domains are different directions. After applying the magnetic field, what happened here? So all domains orient in a field direction. Okay, this is occurs in case of the if you apply the very high magnetic fields. Now coming to the one more thing. So this magnetic field, induced magnetic field increase up to particular value only. So already according to hysteresis loop, we will discuss about this. So that what happened? Induced magnetic field is increases up to particular value, after that it will become saturated. What is the reason means here? So with increasing the magnetic field, all domains are oriented in a field direction. So at a particular magnetic field, all domains already oriented in a field direction. If you increase the magnetic field also, so there is no domains to orient in a field direction. That's why already it is induced magnetic field is saturated inside the material. If you apply the external field also, further induced magnetic field does not increases. Okay, this is the saturation of the magnetization. Okay. So after removing the external field also, so now coming to the after removing the external field also, there are a certain magnetic field inside the material. Yeah. So if you remove the magnetic field also, what happened? So these boundaries already here, if you will take this boundary, so these boundaries are does not change. So boundaries are does not suddenly varies. So that's why, so slowly magnetized material compared to the suddenly magnetized material, slowly magnetized material exhibit retentivity or coercivity value is very high compared to the suddenly magnetized material. So in case of slowly magnetized material, boundary wall displacement will be takes place. That's why, so for demagnetization, so what happened here? So we will apply the very high coercive field, but in case of fastly magnetized material, what happened? So these also will become saturated. It shows high retentivity, but what happened after removing the magnetic field? So may chance to come some domains in their original direction. So not all, some domains may chance to comes to the their original direction. So that's why what happened, this field will be reduces after removing the external field also. Okay, so that's why, so in case of if you magnetize the material, so they will magnetize very slowly. Okay, for preparing the permanent magnet also, so they will made the they will magnetize the, so it's very slowly with applying the very initially they will apply the very less magnetic field, so they will increase, so step by step. Okay, not suddenly. Okay, now coming to the, so after removing of the external magnetic field also, their domains will not comes to the their original position, as well as their boundary also does not comes to the their original position. That's why, so there are certain remnant magnetic field, residual magnetic field or remnant magnetic field inside the material. Okay, so that's why they will exhibit the, they will act as a magnet. After removing the external magnetic field. Okay, now coming to the temperature. What is the dependence of temperature? So if you increase the temperature, the domains are break up and the ferromagnetic substance become paramagnetic. Okay, so this is the process. Why? If you increase the temperature, they loses the ferromagnetism. So if you increase the temperature, what happens at a particular temperature? So those materials suddenly they will loses the ferromagnetism. Those material will become the paramagnetic material. This temperature we will call it as Curie temperature. Okay, above the Curie temperature, the ferromagnetic material will act as a paramagnetic material. Below the Curie temperature, so these material will act as a ferromagnetic materials. Okay, it will, if you increase the temperature, they will loses their ferromagnetism. They will loses their ferromagnetism. This is about the domain theory. So here domain theory will occur. So domains will be oriented by the process of two processes here. So one is the, so displacement of the boundaries of the domains. Second one is the by the rotation of the domains. How those materials will be magnetized means. So here two ways. So one is the boundary. So bound, yeah, displacement of the boundary. Second one is the rotation of the domains. Okay, now coming to the, yeah, This is about the ferromagnetism. Okay, if you have any doubts on this ferromagnetism, I will explain you. So మీకు దీంట్లో ఏమైనా డౌట్స్ ఉన్నాయా? Anyone? Fifth unit. Is there any doubts on fifth unit? అదొకటి స్టార్ట్ చేస్తే ఏమైనా డౌట్స్ వస్తాయి. సో కనీసం ఏదైనా యూనిట్ చదివారా? ఫస్ట్, సెకండ్ ఆర్ థర్డ్? డౌట్స్ ఏం లేవా? So yeah, I will tell you some important questions in this fifth unit. Note down. So I will not tell again and again. So if anyone want, note down these important questions. So first question is the, so first of all we will go to the dielectrics. In this dielectrics, so first question is internal field. Internal field. Okay, internal field, otherwise they will ask a Lagrange field also. Okay, so they will ask whatever local field also. So local field, internal field or Lagrange field. So you have to prove that derivation, total derivation, whatever it will be there, that will come directly to the 14 marks question. 14 marks question. Okay, so second question, second important is the, so on the dielectrics, polarization, types of polarization. So in the types of polarization, no need to write the, so only you have to write the definitions and regarding about the how it will be act as a with temperature. Okay, so temperature తో పాటు అది ఎలా యాక్ట్ అవుతుంది దాని గురించి ఎక్స్ప్లెయిన్ చేయండి. సో దట్స్ ఎనఫ్, నో నీడ్ టు solve the so that means alpha e value, polarizability value is there na, no need to derive that alpha e value. If you have remember, if you already you have any idea, if you by heart that formula means you can write that value formula, otherwise so no need. Okay, alpha e, so electric polarizability alpha e, ionic polarizability so alpha e. Okay, next orientation polarizability and surface charge polarizability. Here four types are there. So those four types, just read the some definitions, how it will react with the temperature. So examples, so adi chadavandi. So that is regarding about the polarization. Now coming to the magnetism. So what are the important questions in magnetism means, so this hysteresis curve. So this hysteresis curve is very important one. So read this hysteresis. So and they will ask combinedly hysteresis and domain theory. Okay, so explain the hysteresis loop while using the domain theory, so otherwise they will ask hysteresis loop. Okay, in this hysteresis loop, so after along with hysteresis loop, they will ask about the, so soft magnetic material, hard magnetic material. So how soft magnetic material will how hysteresis loop will be soft magnetic material. So what is the hysteresis loop for hard magnetic material? So how to magnetize, so which is the easily magnetized, so which is hardly magnetized, so which is having high retentivity, which is having high coercivity. So like that points, so based on that points you will explain the hard and soft magnetic materials, Okay, this is about the, so hysteresis. And one more question in this is yeah, domain theory, hysteresis one, and types of magnetic materials, so para, ferro, dia, ferri, antiferro. Okay, so you have to write these are all. And so examples also, if they ask properties means, so particularly they will mention the properties means you will write the properties. Okay, so depends on the, if they give 7 marks question means, so based on that you wrote. If you give 14 marks question means, so based on that, so based on that you write that. If they ask 14 marks question means write the properties for, so all. Okay, for para, ferro, ferri and antiferro, dia, so for all you have to write the properties. If they ask 17 marks, otherwise sorry 14 marks. If they ask only for 7 marks means, so write the these are all types and give the definitions for each type, definition and some matter. So what is the chi value, what is the mu value, like that. Okay, this is about the hysteresis. Okay, and any doubts on this? సో మీరు ఏ టాపిక్ చదువుకొని వస్తారు? నేను నెక్స్ట్ క్లాస్లో ఏ టాపిక్ మీకు రివిజన్ చేయాలి చెప్పండి. ఏ టాపిక్ డౌట్ ఉంది? విచ్ టాపిక్ యూ హ్యావ్ సమ్ డౌట్స్ ఆన్ దట్? అన్నీ పర్ఫెక్టా? ఎస్. ఏమైనా డౌట్ ఉన్నాయా?
Optoelectrics.
Third unit.
Yes, sir.
So, optoelectronics, I will discuss about that. So only total for starting onwards or only second portion?
Starting is clear, sir. The second portion of like photodiodes and photodetectors.
Okay, yeah. So tomorrow I will discuss about the solar cell as well as photodiode and photodetectors. These all. Okay.
Okay, sir.
Yeah. Any other? So start the reading. You have 3 days. So if you will get any doubt on these 3 days, so I will explain you. Okay. Anyone?
Sir.
Yes. Cheppandamma.
So helium and ruby also from 4th chapter.
Yeah, helium laser and ruby laser. So that is in 4th chapter only. So those
Yes,
are
sir.
the important questions. You want to? Yeah, I will explain you that also again. Okay, helium laser and ruby laser. Okay. And any other? So 3 days are there. So in these 3 days I will explain I will revise this, so everyone should attend. Okay, so 3 4 next up to 9th we have. So there are some holidays will be there. So I think Saturday, Friday, Saturday may chance to holidays are there. So that's why, so we have less time. Okay. Any doubts means, so ask tomorrow. So I will explain tomorrow 3rd unit. So okay, everyone attend that. Yeah, you can leave right now.